Hello everyone and welcome back to Pyman Tutoring. Today we're talking about quantum numbers. Let's begin. So what are these quantum numbers? Well, basically they are like the electron address. And that address is made up of four numbers: N, L, ML, and MS. And you can think of these as the energy level. This is also called the principal quantum number. L tells us something about the shape of the orbital that the electron is occupying. ML gives us information about the axis of the orbital, and MS tells us the spin of the electron. So those are the four quantum numbers. And something called the Pauli exclusion principle, says that within an atom there are no two electrons that have exactly the same address. So each electron within the atom has four unique quantum numbers to describe it. Now let's take a closer look at the periodic table to see how these quantum numbers manifest themselves. When we look across one period of the periodic table, we are basically adding one electron as we read from left to right. Here is hydrogen. Its atomic number is 1. That means it has one proton, and therefore to balance the charge it must have one electron. As we move across, the next element we come to is helium, atomic number 2. It has two protons and therefore has two electrons. Now helium is sitting in group 18 over here with all the noble gases, so it's a particularly stable element. And so what can we say? We start with a hydrogen atom with a proton in the middle, and we've got one electron. And if we think in terms of the Bohr orbitals, we imagine this electron orbiting the proton in some circular fashion. Then we add an additional proton to this nucleus, and with it we add a second electron in that energy level, which gives us helium, and this is stable. So somehow there's a notion that in this first energy level, and we'll call this n equals 1, and notice that is the same as the number of the period that we are in, that this n equals 1 level has been filled up and is stable with just two electrons in it. And now what happens as we move to period number 2, we encounter lithium. So now we've got 3 protons in the nucleus. I'm ignoring the neutrons for now. We know that 2 electrons are already filling the n equals 1 shell. And so we have moved to a new shell in order to accommodate lithium's third electron. And this is the n equals 2 energy level. And again, that is the number of the period that we are in. But now what happens as we go across? We can see that the next element, beryllium, has 4 electrons, And then we have this strange gap in the table before we come to boron with 5 electrons, carbon with 6, nitrogen with 7, oxygen with 8, fluorine with 9, before we get to neon, our next noble gas. So it appears that this n equals 2 level can actually hold a total of 8 electrons. 1, 2 for in there for beryllium, 3, 4, 5, 6, 7, and 8. And similarly, if we move to the third period here, we have a similar kind of pattern. We're adding an electron to the next energy level. So let's say we've got sodium. I won't draw all the protons, I'll just say 11 protons sitting in the nucleus. And then we have, in the n equals 1 level, we have 2 electrons. The n equals 2, we have 8 electrons. And now we have n equals 3, again with 8 electrons. And that takes us to the configuration for argon, the next noble gas. So for some reason we have different capacities for electrons in these various energy levels. And we can explain that in terms of the 4 quantum numbers. So let's look at that. So first of all we have n, which we think of as the Bohr orbital level. That's the principal quantum number. And it can have any integer value we choose. So we looked at 1, 2, and 3, but of course the periodic table goes on and on, so this number continues to grow. That tells us which energy level we are in. Fair enough. Then we have this L quantum number. And it relates to the shape of the orbital that the electron occupies. We call it the angular momentum quantum number. And it can take values of 0, 1, 2, all the way up to n minus 1. So notice that depending on which n level you are in, there is an increasing number of L levels available. So for example, if we are in the n equals 2 level for the first quantum number, then we're allowed to have L values of 0 or 1. The third quantum number, ML, is called the magnetic quantum number. And it takes values that depend on the value of L. So it's allowed to have any value, any integer value from negative L all the way through 0, all the way up to positive L. And that means in the case above, if we take the orbital that has L equals 1, then L equals 1 is allowed to have magnetic quantum numbers of -1, 0, and 1. And the fourth quantum number is the spin quantum number, electron spin. and it is allowed to have just two values, plus 1/2, meaning the electron is spinning up, and minus 1/2 for an electron spinning down. So those are the four quantum numbers and how they relate to each other. And now if we start to look at the permutations of those numbers that we're allowed to have, we will see why the capacity of different energy levels changes and why we get the shapes that we get in the periodic table. Let's take a look at that. Let's take as an example sodium. Atomic number is 11. So we know that we have 11 electrons. We know that sodium is in period 3, so we know that N is equal to 3. Since we have a value of 3 for N, what values of L are we allowed? Well, if you remember, L is allowed to be 0, 1, all the way up to N minus 1. And that means that our L values can be 0, 1, or 2 in the case of sodium. What about our ML values? Well, if we take the L equals 0 case, remember that ML can vary between negative L and positive L. And so if L is 0, the only possible value of ML is 0 itself. When L is equal to 1, however, we can have a minus 1 value of ML, a 0, and a plus 1. So this L level spawns 3 separate sublevels. And similarly, when L is equal to 2, we can range in ML values from minus 2 all the way up to plus 2. And so our L value of 2 spawns a total of 5 separate orbitals for the electrons to occupy. And then finally we have the ms value that simply has a value of plus or minus 1/2. So in this orbital here we have one electron going up and one electron going down. That's the maximum occupancy of this particular orbital. Similarly, if we take L equals minus 1 in this case, again we have a plus half electron can go in there, or a minus 1/2. And so 2 electrons can occupy this orbital. Same here, and same here. And all the way along, each of these ML values corresponds to an orbital which can accommodate 2 electrons. So here we have room for 10 electrons in total. Here we have room for 6 electrons. And here we have room for 2 electrons. And this is why we have the blocks that we see in the periodic table. When n is equal to 1, up here, we only have one orbital that the electrons can occupy, and that's the n equals 1, L equals 0 orbital. 2 electrons will go in there, and so that first period is full when we get to 2 electrons. If we go to the second period, however, and we look across, now our n is equal to 2. Our L values can be 0 or 1. Our ML values can be 0, -1, 0, +1. And in each of these we have a total of 2 electrons. So 2 here, 2 here, 2 here, and 2 here. And so we see that it takes 8 electrons to make our way from the left to the right-hand side of the periodic table. Let's take a look at the shape of these complicated orbitals. First of all, let's distinguish between orbits and orbitals. In the Bohr model, we were dealing with fixed orbits for the electrons. We refer to it as the planetary model because it looks like planets orbiting the sun. And the concept is of electrons being well-defined particles rotating around the central nucleus in circular orbits. When we moved into wave mechanics and quantum mechanics, the concept of an orbital was introduced. And here we're talking more about electron clouds. And by that we mean that we can only talk about the probability of finding an electron at a certain location. We cannot know the exact location of the electrons and their velocity at the same time. That's called the Heisenberg uncertainty principle. And so the concept is of more fuzzy dispersed electrons forming electron density clouds. And so these diagrams now of the orbitals that the electrons occupy are much more cloud-like in nature. Let's start with the L equals 0 shape. And this is called an S orbital. And these are spherical in shape. So if we draw a set of axes, and we think of the electron cloud as being some kind of fuzzy sphere. Try and imagine this in 3 dimensions if you can. And so we know that when L equals 0, ML equals 0. And now MS can be plus or minus 1/2. And that corresponds to 2 electrons as the maximum occupancy of any given S orbital. And as the value of n increases, the size of the S orbital increases. The electrons spend more time further away from the nucleus when n is larger. So we can think of this orange as n equals 2, L equals 0. Whereas the yellow would be n equals 1, L equals 0. Now if L is equal to 1, we call this a p orbital. And rather than being spherical in shape, these are like dumbbells. So we can sketch them in this kind of fashion. So if you imagine these are the x, y, and z axes, then one dumbbell will be aligned with the x-axis in this fashion. And remember, this is the electron density cloud. And this we call the px orbital. There's a py that aligns itself with the y-axis. And of course there's a pz. aligned with the z-axis. And remember that if L is equal to 1, then ML can be equal to -1, 0, or 1. And these three values correspond to these three orbitals. Each of these can accommodate 2 electrons, so we can put a +½ and a -½ in here, +½ and -½ in here, and a +½ -½ in here. And as a result, 6 electrons. Now when L is equal to 2, we have something called a d orbital. And these are kind of cloverleaf shaped. And there are 5 of them versus the 3 dumbbells. They get a little harder to draw, as you might imagine, and I will do my best, but I make no promises. So we have a cloverleaf in this plane, cloverleaf in this plane. So this would be YZ, this would be XY, this would be XZ. There's a dx squared y squared that aligns with the axes, and then there's a dz squared, which is a really odd one, aligns with the z-axis, and there's actually a donut that goes around it. So those are the 5 different ML values that originate from an L equals 2 quantum number. Remember, ML varies from -L to +L, so we have a -2, a -1, a 0, a 1, and a 2. And those are our 5 orbitals shown here. And again, each one can have an up electron and a down electron, so we put ±1/2 into each of these, and thereby ending up with a total of 10 electrons, which can fit into the L equals 2 orbitals. Now L equals 3, we don't deal with them much at this level of chemistry, but L equals 3 is referred to as an F orbital, and there are 7 of those, because if L is 3, there are 7 possible values of ML. 7 possible MLs, each accommodating 2 electrons. That means we have room for 14 electrons in the L equals 3. That's the F orbital. And that's 14 electrons. I won't attempt to draw the shapes of those. So hopefully that's starting to make sense now, why we have the various blocks that we do in the periodic table, as these various quantum levels are filled with electrons. Let's go over all the rules governing these quantum numbers. So energy level N contains N sublevels. That is, when N is equal to 1, we only have L equals 0, and that's the only sublevel we have. So 1 sublevel. When N is equal to 2, we say that L can be 0 or 1. And so we have 2 sublevels. When n is equal to 3, L is equal to 0, 1 or 2, so we have 3 sublevels. And remember, here when we're talking about sublevels, we're talking about sub-energy levels. So we're saying that within the n equals 2 level, energy level, there's actually a splitting of that level into 2 different levels, slightly different energies. The s orbital and the 3 p orbitals. And there's an energy difference between these two. And when n gets to 3, we're saying that there's an s level energy, there's a p level energy with 3 spaces, and there's also a d level energy with 5 orbitals. And that's what we mean by these n sublevels. So number 2, each L sublevel may be split into multiple degenerate orbitals. And what do we mean by that? Well, the word degenerate in this case means that they have the same energy. Degenerate levels have the same energy. So these 3 p orbitals here all have the same energy. These 5d orbitals all have the same energy as each other, and so they're referred to as degenerate energy levels. And these degenerate orbitals have different ml numbers. And then thirdly, each ml orbital can accommodate only 2 electrons. Now, rule number 4 is called the Aufbau principle. And the Aufbau principle simply says that the orbitals fill according to an increasing level of energy. So you fill the lowest energy orbitals first, and then keep adding electrons at the lowest possible energy level orbital available to you. Now you might think that simply means filling up according to the n values, but it's not quite as simple as that. And the best way to deal with this is to memorize this simple table. So we have the n equals 1 level, and that's an s orbital only, and it can accommodate 2 electrons. The next highest energy level would be the 2s when n is equal to 2, and again that can accommodate 2 electrons, but we also have a 2p level which contains 3 orbitals, each of which can hold 2 electrons, so that fills up at 6. Then we write 3s, again there are 2, 3p can hold 6, and 3d can hold 10. We usually stop at 4, so 4s2, 4p6, 4d10, and here we have 4f14. So if you can write this simple table, then you can easily see the sequence in which the energy levels should be filled. And basically you use the diagonal. So here we have 1s2 being filled first. The next diagonal takes us to 2s2. Again, coming in on the diagonal, 2p6 fills up, and then 3s2 fills up, and then 3p6 fills up, followed by 4s. And notice the subtle change in sequence here, that the 4s is filling up ahead of the 3d. So that's why this table is useful, just to remind you of that subtle sequence change that occurs. So we have 3d filling up, and then 4p6, and in fact this would carry down to 5s next. So that's the Aufbau principle, that's rule number 4, so remember that little table. Rule number 5 is the Pauli exclusion principle. And basically we've already stated this at the beginning of the video, that no two electrons can have the same 4 quantum numbers. In an atom. And rule number 6 is called Hund's rule. And this basically says that electrons remain unpaired unless they have to pair up. So electrons prefer to be unpaired. So if you have the option to fill degenerate levels, remember degenerate levels means orbitals with the same energy, you have the option to fill them with single electrons or pair those electrons together. Then the electrons prefer to be unpaired, and we'll show some examples of that to make it clear. So those are the 6 rules. Now let's look at some presentation formats that are used for showing electron configurations. So the simplest one is just a sequence. And so, for example, if we had phosphorus with an atomic number of 15, we know we have 15 electrons to distribute into their orbitals, and so we simply write out the list according to the Aufbau table. 1s2, 2s2, 2p6. So far we have placed 10 of the 15 electrons. After 2p comes 3s, which accommodates 2 electrons, and 3p, which could accommodate 6. Now we only need 5 more to complete phosphorus, so we're going to put 3 in here. So our p level is just 1/2 of its maximum capacity. So that's the simple sequence. There's a shorthand version of that, which is called the noble gas format. And the noble gas format simply says a whole bunch of this electron configuration here, specifically this piece here, 1s2, 2s2, 2p6. That is the electron configuration of the noble gas neon. And so instead of writing out the entire electron configuration, we can write shorthand, put the noble gas, and then simply list the additional electrons beyond the relevant noble gas format. And incidentally, this last group of electrons here in the highest energy level, N, these are our valence electrons. Okay, the third format is actually an energy level diagram. And this is perhaps the most useful in terms of showing information. So here we write all the s orbitals in a column, all the p's, all the d's, all in separate columns. And their height on the chart indicates their energy level. So we start at the bottom at 1s. Higher energy is the 2s. And we move over here to show the p, and we show the 3 degenerate levels in 2p. Then we come back to 3s, and then slightly higher energy level we have the 3p. And that's as far as we need to go in this particular case for 15 electrons. And now to show the electrons themselves, we simply use an up and down arrow on each of these orbitals. So there's 2 electrons in the 1s, one up and one down. One up and one down in the 2s. The 2p is full. The 3s is also full. And now we have the 3p3. So we've got 3 electrons to put into these 3 orbitals. And here we invoke Hund's rule that says the electrons would prefer to be on their own if they can be. So we put in all the up electrons first. And there's our 3p3. And this is 3 unpaired electrons. Our fourth and final format is to use an orbital diagram. So this simply shows the orbitals as boxes. This would be 1s, 2s, 2p with its 3 suborbitals, 3s, and 3p. And the electrons are shown in exactly the same way. So 1s is full, 2s is full, 2p is full, 3s is full, and then 3p is half full. Now let's just take one more look at the periodic table before we get into some examples to solidify these ideas. So just one quick last look at the periodic table. We know that over in this section we are filling the s orbital, and so this is called the s block. Over here on the right hand side these 6 groups, this is where we are filling the p level orbitals, and so this is called the p block. This section in the center is where we're filling the new d orbitals, and so this is the d block. And down here at the bottom, this is where the f block comes into play, where we're filling the f orbitals. So one thing to notice, we did talk about that Aufbau table. Let me just write it again. So we've got 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. You'll memorize this soon enough. 4s2, 4p6, 4d10, 4f14. Remember, the Aufbau says fill diagonally, and that all looks perfectly logical until we get to this point here where we fill 4s before we fill 3d. And so that leads to a little bit of a quirk in the periodic table. So down here where the very first D block elements appear. We said previously when we were looking at the first three periods that this number of the period corresponds to the n number for that particular quantum level. But these guys here, we are actually filling the 3d10 level here, even though we are in period number 4. We're moving from the 4s, calcium, 4s would be potassium and calcium, and then the next elements in the periodic table, this would be starting with scandium and titanium. So even though we are in period number 4, we're actually filling the 3D orbitals. And that continues through. Whenever you're in the D block, you are always one index behind in terms of n. And in fact, when you get down to the F block elements, you end up being 2 indices behind. So you start filling up the 4F when you're actually in period number 6. Okay, so that's just one quirk to watch out for. And as long as you remember your Aufbau table, you should be just fine. Now, without further ado, let's do some examples and solidify all this information. Okay, here we go, some examples. Number 1, let's do the electron configuration for sulfur. The atomic number for sulfur is 16. And so we can write this in sequence format. 1 s2 electrons, 2 s2 more electrons, 2 p6 electrons, 3 s2 more electrons. We've got 4 more to place, so 3p only has 4 electrons in it. So that's the electron configuration for sulfur. We can also write it in noble gas format by taking this first section of the configuration and replacing that with neon, and we're left with 3s2, 3p4. Now we take a look at a couple of ions. Now remember, when we're dealing with ions, we are either adding or subtracting electrons from the electron configuration. So let's suppose we have the sulfur 2- ion. So the atomic number is still 16, but the number of electrons is 16 plus 2. So we've got 18 electrons altogether. And so our configuration is the same as for the atomic sulfur, except that we have 3s2 and 3p is now 6, with those 2 extra electrons to take us from 4 to 6. Let's look at another ion, Al3+. So here the atomic number for aluminium is 13. Now the number of electrons, we've got a 3+. That means we've lost 3 electrons, and so we only have 10 electrons to place. And so we have 1s2, 2s2, 2p6 as the electron configuration. Okay, this one we come from a slightly different angle. We want to know the 4 quantum numbers for the 3d8 electron. We know that the first number is the n quantum number, so we know n is equal to 3. We have a d-shaped orbital, and that means that L must be equal to 2. And therefore the ml values range from -2 to +2. And there are 5 of them. 1, 2, 3, 4, 5 orbitals. 5 degenerate orbitals to fill. And we're looking for the 8th electron in that particular degenerate set of orbitals. So if we fill this according to Hund's rule, we do all the ups first. 1, 2, 3, 4, 5. And then 6, 7, 8. So this is our 3d8 electron. And its quantum numbers are therefore n equals 3, L equals 2. It's sitting in this middle degenerate orbital where ml is equal to 0. And it's the second electron to go into that orbital. And so, since the first one was an up, this one would be a down. And there you have the 4 quantum numbers for the 3d8 electron. Let's have a look at a quirky one. Number 6. Cobalt. So cobalt has an atomic number of 27. And so we're looking to place 27 electrons. And so we can go through the longhand version, 1s2, 2s2, 2p6, 3s2, 3p6. Remember now 4s2 comes next from the Aufbau table. And then we've got 7 more electrons to place, so we say 3d7. And in shorthand we can choose the highest atomic number noble gas below that, which would be this guy here, which is argon. And so we could write this as argon with a 4s2 and a 3d7 added on the end. So cobalt is okay, but what about the cobalt ion? Specifically cobalt 2+. So now we've got the same atomic number, but the number of electrons we have to place, we've lost 2, so we're down to 25. Well, where do those 2 electrons come from? So you might intuitively go to the highest energy level and say that 2 of these 7 electrons are the most likely to be lost to ionization. But as is often the case in chemistry, we have an exception. We actually always remove electrons from the highest N level. And so in this case, cobalt 2+ actually becomes Ar3d7. The 4s2 electrons are the ones which are removed. Let's look at a couple of elements that are also exceptions. Chromium is a common one. Chromium has an atomic number of 24. So we're dealing with 24 electrons. And so we might expect an electron configuration of argon, and then we've got 3 electrons less than cobalt. So we might expect 4s2, 3d4, based on the Aufbau table. But this is not correct. In fact, one of these electrons from the s level goes into the d level to change this to a 1 and this to a 5. And why does that happen? Well, if you remember, the d level has 5 degenerate orbitals in it. And it turns out that there's some unique stability to the case where there is one electron in each of those orbitals. And consequently, one of the s electrons is happier if it's sitting here in the 5th d suborbital. So that's an exception. The other common one is copper, where we have atomic number of 29, so we're trying to place 29 electrons. And if we add 5 electrons to chrome, we might expect this configuration: 4s2, 3d9. Again, we have our 5 degenerate d levels. We're trying to place 9 electrons in there. Well, that leaves one empty space, and it turns out that the atom is happier if that 10th electron joins the other 9, and we leave an unpaired electron in the s level instead. So we end up with 3d10 4s1 instead. So those are two specific exceptions based on unique stability configurations in the d level. So just be aware of those. So that's about it for this video. Hopefully you now have a good idea of how to write electron configurations of any atom. You understand the 4 different quantum numbers associated with an electron, and also a little bit about why the periodic table has the unique shape that it has. If you found this video useful, don't forget to like and subscribe. Click on the bell if you want updates when new videos are posted, and I'll see you next time. Thanks very much.